Welcome to this session of the IAMP One World Seminar. For the people who are new, this seminar is organized by the International Association of Mathematical Physics. It takes place on Zoom more or less every 2 weeks. And if you don't know the IAMP, you are very welcome to visit the web page. You will see the program of the seminar and also all other activities of the association. So today we have the pleasure of having Thomas Leblé from Université de Paris-Cité, and he's going to talk about recent progress on the two-dimensional one-component plasma. So thank you very much.
Thank you very much for the invitation. I just remembered that I think I participated to this seminar 5 years ago. I was the opening act for Silvia Serfati during COVID. So I'm happy to be back in non-COVID times where it's just for fun that we meet online and not because we have to. I will present the 2D OCP, so the two-dimensional one-component plasma, and some questions around it and some recent progress, but as you will see, there's still a lot to do. I don't have a particular theorem that I want to prove, so feel free to interrupt at any time, and my goal is mostly to get you to introduce the model if you don't know it, and to get you interested in it, or to and to explain why it has many interesting features. So what is the 2D OCP? It's a model of statistical physics. And the basic setup is the following. You have n particles, which are the purple things here, which you think in physical terms as point charges. And they live in this big box of radius square root n. So I will take my box will be a disk. If you want your box to be a square, that's also fine. The physicists, they often take a square because it's more natural for them. It doesn't really matter for almost all questions that we're going to study. And in that box, you also place what the physicists called a continuous neutralizing background, which is just a constant density of charges with the opposite sign. So if the purple things have +1 charge, the blue thing has a density -1. And so you end up with a system which is made of two parts. You have the positive part, which are the point charges, and then you have the Lebesgue measure on the box, which has the opposite sign. Overall, it's a neutral system. And this is the fundamental observable, the fundamental object. Of course, since the Lebesgue measure doesn't change, the only variable is here. And sometimes I will just write it down as big Xn minus dx. And you should keep in mind that everything takes place for the moment in one box. Okay? And so I will, in particular, I will represent this measure of the charges with big Xn. So that will be the state of the system, because the continuous background it's always the same. And when you fix the state of the system, then the next thing you want to do is to define the energy. And since, well, it's the nature of the 2D OCP is that the energy is a Coulomb interaction energy, denoted by a big Fn. And here's how it looks like. So in 2D, as you may know, the Coulomb interaction is -log up to a constant. So you will take the pairwise interactions with the -log potential between what? Well, between the system and itself. And the system is the positive charges minus the neutralizing background. So you have this against itself. And the only thing that you do is that you remove the diagonal because you don't want a point charge to interact with itself. That would be bad. And you restrict to the points in the box. So Xn lives in the box, but the Lebesgue measure, you make sure that you only look at it within the box. So that's the energy for a given state of your system. And then you do the usual statistical physics procedure. You fix the inverse temperature, which I will denote by beta, and you define the canonical Gibbs measure, which is as usual. So the main thing is the Boltzmann factor, E minus beta times the energy. This is the Lebesgue measure on the box tensor N. Okay, so the reference measure, if you want, is just taking all the points uniformly within the disk and independently, and then you have this density that, of course, makes them very much non-independent. And you divide by whatever needs to be here so that this has mass 1. So this is the partition function. And in a sense, that's the 2D OCP is this measure on n tuples of charges within a box. And it depends on beta, it depends on n. This is the finite volume 2D OCP, to be precise. Before I go on, some related models. So you could argue, why are we doing 2D things? Physics in 2D is not very natural. So you could look at the 3D OCP with the Coulomb interaction in 3D, which is the usual Coulomb interaction, 1 over the distance. Or you could even do higher dimensional Coulomb gases, so higher dimensional plasma, and the Coulomb interaction in higher dimension is given by this. If you really like to stay in 2D, there is another model that you could look at, which is the 2D TCP, so two-component plasma. And that's sometimes also called a Coulomb gas. So my policy recently has been to call the model I'm talking about the 2D OCP and not the Coulomb gas, because Coulomb gas is kind of ambiguous. You have, depending on whom you're talking to, it will mean different things. In the physics literature, that the Coulomb gas is usually it's often this two-component thing. What is the two-component thing? Well, you have plus charges and minus charges. You don't have the continuous background. The continuous background is replaced by n negative charges. In a sense, well, there's an extra difficulty here, which is the fact that the +1 and the -1, they really want to be close to each other. In particular, the system is not defined for all values of beta, and that creates additional difficulties. But in another point of view, more is known about this system than about the 2D OCP. So whatever you play with really depends on your taste. There are things called a hierarchical model. I won't go into the details. If you know what a hierarchical model for spin systems is, well, it's kind of the same, but with the point charges. And if you don't know, that's fine. I won't talk about it anymore. And of course, you could define, instead of placing yourself on a disk, you could want to work on a sphere so you don't have boundary effects, or on a more general manifold. But I will stick to the disk. So why do we care? Well, it depends on your taste again. You could treat this as a toy model for matter, and I think that's partially what was the point of view in the 70s, 80s. Another point of view would be, well, if we want to do statistical physics in dimension 2, because dimension 2 is interesting, it's more complicated in the dimension 1, but not as complicated as dimension 3 in a sense. Well, the Coulomb energy is a natural energy to look at, so that's a natural model to look at. And in particular, the question of whether you can prove phase transitions in this model and phase transitions in 2D in general is an interesting question on which I will come back later. The fact that you have logarithmic interactions between these charges also appears in different contexts. For example, in vortex systems, or fluid mechanics, or in Ginzburg-Landau models. So that's, I did my PhD with Silvia Sarfati, and that's where she came from, in the sense that studying Ginzburg-Landau equations led her to study those vortex systems, and then those logarithmic interactions, and then the 2D OCP. And then there are other connections with the fractional quantum Hall effect. You could be interested in trying to minimize this Coulomb energy, which leads you to questions about non-random constructive approximations. And then I will give examples of other models that place this model in a wider family of models of stochastic geometry in 2D. And I should also mention, so this is 2D. You may know the log gas in 1D. The log gas in 1D looks very much the same as this, except that you're in 1D, you're on a line segment instead of being on a disk. Okay? And in 1D, this logarithmic interaction and this log gas has connection with random matrix theory. There's a tiny bit of connection in 2D, but really not as much, not nearly as much as in 1D, so I don't spend too much time on this. Okay, so what do physicists think happens in the model? So let me remind you that this is my model. In a sense, this is the Gibbs measure I'm looking at. So first question, what about when the temperature is 0, so beta is plus infinity? When beta is plus infinity, you're focusing on the minimizers of Fn. That's not difficult. The fact that you're focusing on energy minimizers is not difficult to understand. Understanding the energy minimizers is extremely difficult. So what is conjectured to happen is that the minimizers, they form a triangular lattice or hexagonal lattice. We are extremely far from knowing that. Funnily enough, if you ask the same question in dimension 8 or 24, so for Coulomb gases in dimension 8 or 24, now we know the results because the breakthrough that Marina Wiazowska did, and for which she got the Fields Medal, about universal optimality in dimension 8 and 24 also apply to Coulomb gases. So we know that certain lattices in dimension 8 and 24 are the energy minimizers for the Coulomb energy, but in dimension 2, we are not able to prove yet that the hexagonal lattice is indeed the energy minimizer. But numerically, it seems very clear, and I think everyone believes in it, but there is no proof or even something close. So the plus beta equals plus infinity situation is conjectured to be a lattice, but we don't know how to prove it. And then on the other hand of the spectrum of the range of parameters, when beta is very small, the physicists think there's a liquid phase. What that means, it means the correlations decay fast. You have lots of invariances, translation, maybe rotations. And then somewhere in between, and numerically in the 80s, there was a series of papers pinpointing that the value should be around 140. There is expected to be a phase transition, which they call crystallization, and the nature of which is a bit unclear, but basically you would go between a liquid phase and something that is closer to a lattice. So if I draw this phase portrait, and let me emphasize that for the moment, almost everything is a conjecture. And this is beta. Okay, so the inverse temperature. Well, let me start from here. You would, so that's temperature 0. You would be a lattice. Exactly here you're a lattice. Here you're a crystal, which means something close to a lattice, but not exactly a lattice. I can be more precise. So I think what they mean is that you have long-range correlation of the angles between the particles, but no long-range correlation of the positions. And then around 140, you move into a liquid phase, so that beta goes down and then the temperature goes up. And then here you're the liquid phase. Beta equals 2 is the integrable case for which we know basically everything because it has connection with random matrix theory. And then when you reach beta equals 0, so that's infinite temperature, well, the interactions do not matter and you only have IID points. Okay, this part is the only thing we know. Okay, when if you take here beta equals 0, well, this doesn't matter and you only have IID points. So that's known. And then the rest is a conjecture. And beta equals 2 is a special case for which we know how to compute things. And indeed, for beta equals 2, you're liquid. But whether you're a liquid for beta equals 2 minus epsilon is not known. Okay, so that's the main goal that we would like to reach, and that's why we study the system, is to understand this phase portrait better. There are other things on the way that we are interested in. Okay, the first sort of basic question is, I have a finite volume model. Does this have a limit as n goes to infinity? Because again, as you probably know, phase transitions, they are only really appearing in the infinite volume limit, right? So it would be good to know that you have some kind of infinite volume limit to work with. So if I write my finite volume model again, this is the law of an n-point point process, and I would like to derive some kind of limit for it. Okay, so I can look at each block. This is n points ID in a big disk. Okay, this has a limit, so to speak, which is a Poisson point process, which is an infinitely many points in the plane. ID, if you want. Okay, so this is fine. The fact that the partition function has a limit in that sense, log kn divided by n converges to a constant, was known for a long time. That's a result of Sari Merlini, I think, but building on Lieb-Narnhofer. They don't know which limit it is. It's just an abstract argument showing that this must have a limit. So this has a limit in that sense. This has a limit. And then the fact that you can give a meaningful limit for the Coulomb energy was really non-trivial, and that's one of the first big achievements of Sylvia and Etienne Sandier in that domain, is they define what they call the renormalized energy, which is the right object to take the limit of Fn as n goes to infinity. So of course, it won't be just Fn, it will be Fn divided by n converges to some functional on infinitely many points. And maybe one thing I should have said earlier is why, on a purely mathematical point of view, why is this system difficult/interesting, or difficult hence interesting to study, is that the Coulomb interaction, the minus log in 2D, is long range. It does not decay fast at infinity, which means in particular that it's hard to give a meaning to the interaction energy of infinitely many points, because really everyone talks to each other in a sense, at least a priori. So it needs special care to study the infinite volume limit. Okay, so that's one belief. The physicists, they don't even really ask the question. The physicists, some of the papers just start by, let us consider an infinitely extended 2D OCP. But whether that exists is not completely clear. Another belief or result in the physics literature is that those systems exhibit what they call cancellation of charge fluctuations. So what does it mean in our setup? So let me go back to for the moment, we only know the finite volume model. Okay, so let's go back to the finite volume model. The diameter is square root m, or order square root m. Let me take some point x not too close to the boundary, so somewhere in the bulk, and then a big disk around x, and I will compare the number of points within the disk to the surface of the disk. Okay, and I want the typical size of this, which actually is the same as just looking at the variance. Well, if I want the typical size square, if I want the second moment of that quantity, number of points minus area, it's like taking the variance. And the physicists say that this variance, if you look at it when r grows, it grows much slower than r squared, which is the area of the disk, and actually it grows like big O of r. The thing we should have in mind is that if I take ID points, of course, I will have somewhat r square points here, but the variance will also be r squared because the variance of a Poisson of parameter p is also. So, so that's why they say it's cancellation, because this grows much smaller than it would be for ID points. And not only is it much smaller, but actually they say it's like the perimeter. The variance is like the perimeter. And there's a theorem that says you cannot do better. Even if you take a lattice and you count the points that fall into a disk, you will not do better than this. Okay? So, so this cancellation of charge fluctuations is also, sometimes it's called hyperuniformity. It's another property of the system that the physicists were very interested in the 80s. There is a series of papers devoted to it. That's what I meant. I didn't write the references, but I'm happy if anyone is interested at the end to think of them or send them by email if you're interested. Another belief, well, or belief or disbelief. Sometimes when you talk about this, someone says, well, for sure there is no phase transition in your model because there is no phase transition in dimension 2. Or another way to say it is that there is no symmetry breaking in dimension 2. And that's the Mermin-Wagner theorem. So first of all, I've learned not so long ago that this should really be called the Mermin-Wagner-Hohenberg theorem because he proved it slightly before and in the case that is usually used now. So let's pay tribute to Mr. Hohenberg. And let me emphasize the second thing is that it's a theorem, so you have assumptions. And if the assumptions are not satisfied, you might not have the conclusion. So what is the theorem? Is that if in your system you have continuous symmetries, for example, translations or rotations, okay, and you have certain assumptions on the interaction, then the symmetries will be preserved when you pass to the n equals plus infinity limit. But you need some assumptions on the range of the interactions, and typically Coulomb does not satisfy the assumptions. So it's unclear whether this theorem applies or not to the 2D OCP. So it's not clear whether we can say this or not. What I will explain later is that it does apply for translations. The translations are not broken for the 2D OCP. What about the rotations? Well, we don't know, and it might actually be the phase transition that the physicists believe in might actually be about this. It's for the moment it's unclear. Okay, so these were the physics questions. Let me add some more questions which are more mathematical, so maybe the physicists would not be so excited about them, or just reformulation of what I've just said. Okay, so existence of a limit process, it's something I've talked about. You could be a mathematician and say, okay, well, maybe there is no limit, but there are limit points to this model. Okay, so maybe it doesn't converge, but up to subsequences, that would already be good. When you take the infinite volume or the thermodynamic limit, so n goes to infinity. Second question, if there is a limit or a limit point, can you describe it in a nice way? So something that would look a little bit like this. In finite volume, that's exactly how it looks, right? The Gibbs measure is exactly of this form with an n here. Okay, what about when n goes to infinity? Can I describe the process as E minus beta times an energy times some reference measure? So we'll see, you may already know the answer. The answer is not exactly like this, but maybe in a slightly different way. And then the symmetry breaking question is, okay, if I have this limit process and I can describe them, can I prove that they are translation invariant or rotation invariant, that is the symmetries that are not broken? The thing about charge fluctuations is there's a whole community devoted to the study of hyperuniformity, which is really proving that this grows smaller than r squared. And so hyperuniformity is the variance of the number of points in a box, which is a non-smooth statistics. You're really taking an indicator function against your system. You could replace the indicator function by smoother test function and ask, how does the variance grow? So that's not something that is really discussed in the physics literature, but it's been discussed in the mathematics literature quite a bit in like 10 years ago. Okay, and let me add two, maybe just one, because time, well, was two questions which are from of more mathematical nature. The first one, I don't know if some of you might be familiar with it, but I assume that not everyone is the question of rigidity à la Gauche-Perez. So it refers to a paper of Gauche and Perez in 2012, I think, where they were observing this phenomena for certain point processes. So the basic question when you study rigidity à la Gauche-Perez is the following. You have your infinite process, and then you take some finite domain lambda, and you hide what's inside lambda. You just observe what's outside lambda. And the question is, from this observation, what can you say about what's inside lambda? Can you say how many points are inside lambda? If yes, you say that the process is number rigid. Can you say, moreover, what's the barycenter? What's the center of mass of those points? If yes, you say that the process is center of mass rigid. Can you say everything? Can you determine exactly where the points are? If yes, you're fully rigid. And there is a whole hierarchy of rigidity, and of course, deterministic processes, they obey all these rules. But the fun part is that you have highly non-deterministic processes which have certain of these properties, but not all of them. So that's another feature that some processes have, some other have not, and that sort of puts them in a hierarchy of how rigid you are. And then let me briefly explain what I mean by this last question, the transportation distance. So the question is how, and if you don't like this, just wait for 2 minutes and then I will go back to a different topic. The question is, can you evaluate the Wasserstein distance between your points and the Lebesgue measure? And the motivation for this question is the following. So here it's maybe not super smart. I'm scaling back everything to size 1 just for this slide. If you take a disk of size 1 and you put NID points, okay, and you look at their empirical measure, and then you compare it to the Lebesgue measure on the disk, and you ask, how does the Wasserstein distance grow when you add more and more points? And I think I am missing a normalization somewhere, but maybe to what I want to say is that, so this question, of course, you can ask it in dimension 1, in dimension 2, in dimension 3, right? You replace the disk by a line segment or a disk, or a ball, sorry. The point is that if you're computing average Wasserstein distances between empirical measures and the continuous version, so the Lebesgue measure, precisely in dimension 2, you see that ID points have some growth. It's log n to some power, which lattice points do not have. Okay, so typically for this question, you see the difference between ID points and lattice points. And so if you sample points which are neither ID or lattice, and you look at this quantity and you look at how much it grows or not, then you can say whether they are more like ID or more like a lattice. Okay, and precisely if you don't have this growth, if this is bounded, then you're more like a lattice. And if you do have a growth, then you're more like ID, you're more disordered. Okay, so it's just, this question is another way to characterize whether a process is ordered like a lattice or disordered like IID points. Okay. So let me close this parenthesis. This was just another type of question you can ask. And sorry, before actually talking about the 2D OCP, because it's more fun to see it among a certain family of processes. Let me talk about some of his 2D friends, okay? So other point processes in 2D, which have interesting behaviors of whose behavior we can interestingly compare to the one of the 2D OCP. The most basic one is the Poisson point process. The Poisson point process is the closest we have to infinitely many IID points, okay? So the definition is if you take a bounded domain, the number of points in this domain is distributed as a Poisson random variable. And then if you take of parameter the volume, and then if you take two domains which are disjoint, then the number of points in those domains is independent. The Poisson point process, what I write in blue is what's the connection or the informal connection with the model. That should describe the model roughly when you have very high temperature, so beta is close to 0. You're expecting to see a lot of points which do not talk to each other. Okay, so that's one extreme. Another extreme is the stationary lattice. So instead of Z2, maybe you can take a triangle or lattice, but it doesn't really matter. It's just an image, right? So you have something very ordered, and the only randomness you allow is you shift the origin uniformly in the unit square. So you don't really see a lattice. You see a lattice up to the, well, you see a lattice, but maybe there's not a point at 0, right? That's the only randomness you allow. And that should describe, as I said at the beginning, whether it's Z2 or the hexagonal lattice, something very ordered should describe what happens when beta goes to infinity. And then you can add some more randomness. So you can take this lattice and then perturb it. You could take IID perturbation. So each point you move it by an IID displacement. Or you could take correlated displacements. And that could describe what happens when beta is very large, but not exactly infinity. So you start from a lattice and then you start moving a little bit around. Okay, so those are models from stochastic geometry, which are interesting to compare to the 2D OCP. And then there are two actual models, which are closely related to the 2D OCP. One, which some of you might know, is called the zeros of the Gaussian entire function. What is the Gaussian entire function? It's this. You take a bunch of IID complex Gaussian coefficients, and then you form this power series. It's not hard to see that it converges almost surely. So it has a infinite radius of convergence. And so you could look at the zeros, and they form a random point process in the plane. This is called the zeros of the GF, and this has been studied a lot by Tzirelson, Sodin, and then there's a big community in Israel studying those functions. Okay, so they form a class of 2D point processes, and this one is one example. Okay, and finally, the Ginibre ensemble. So what is the Ginibre ensemble? You take a matrix with IID Gaussian coefficients, complex Gaussians, okay, and they are IID. There is no symmetry in your matrix. You look at the eigenvalues, and almost surely it has n eigenvalues in the complex plane. Okay, it turns out that those eigenvalues are up to a minor difference in the definition of the model, distributed like a 2D OCP with beta equals 2. Okay, the minor difference is that in my model, the points have to be in the disk, whereas these eigenvalues, they don't have to be in the disk. They will be in the disk for 99% of them, and then some might be just at the boundary. It's a very minor difference, and you can switch from one to another. But basically, you can just keep in mind that beta equals 2. The reason I said it was integrable is that it has this connection with random matrix theory, and this, for those of you who know what it means, is a determinantal point process, which means that most of the questions you're interested in can be, in principle, attacked by a computation. Whether you can actually do the computation or not is a different question, but actually you have many more answers in that setting. Okay. And so let me go back to the phase portrait, maybe in a more mathematical perspective. And again, this is zero temperature, this is infinite temperature. This should be a lattice, we don't know. This is Poisson, we know. This is Ginibre, we know. And the question is, so Poisson is disordered. A lattice, hypothetically, a lattice here is very ordered. How does the order evolve as we move from Poisson to a lattice or the other way around? And well, the sad part or the interesting part is that for the moment, no order parameter has been found to change really significantly as you move from 0 to plus infinity, if you exclude 0 and infinity at least. And the fun part is that it seems that everywhere there is order. So in all the notions of order that I've introduced, they are all satisfied across the whole range of parameters, if you exclude, again, 0 here. So that's a little surprising. But okay, that's also what makes the model interesting. So before, yes?
I have a question. So is this what also physicists believe? So don't they have anything like behavior correlation function or whatever, which distinguishes between the two phases?
Well, so thank you. That's actually a good point, is that they do believe that correlation functions would change their behavior from here to here.
Okay.
But as I will show, these notions of order that we can study are kind of different from the usual order. And you will see in a minute. What is interesting about those notions of order is that it's kind of order within disorder. You may have very disordered looking correlation functions, and yet when you ask actual questions to your system, it is very ordered. So you will see. But the physicists, they do think that the correlations should change. But okay, so maybe what I could say is that obtaining the correlations is very difficult. So except for beta equals 2, we have no understanding of the correlations. The only questions we can ask are one of those questions that I presented. And for those questions, well, sometimes we can answer. But the fun part is that it seems that everywhere on this range, you have order.
Okay.
So let me just remind ourselves of the two extreme cases, the Poisson and the stationary lattice. Let's forget about this part, okay? Which we should keep in mind as order and disorder. Okay, so for a lattice, you have long-range correlations, obviously. It is very much hyperuniform, so it has cancellation of charge fluctuations, if you want, and that's as good as it gets. The variance in a disk of radius r scales like r. It is very rigid in the sense of Gauche-Perez. Well, if I show you a lattice and I hide a little part, you can probably reconstruct what was in the hidden region. And regarding this thing of distance to Lebesgue, if you followed me on this, it's also as good as it gets. It's bounded when the number of points. Okay. And then on the other hand, we have the Poisson model, no correlations whatsoever. Okay. The number variance does not scale like R, it scales like R square. There is obviously no rigidity. If I show you a Poisson point process and I hide a region, you cannot tell me anything about what's inside, because everything is possible. And the distance to Lebesgue is not big O of 1, it's plus infinity. It just means that, okay. Maybe I didn't explain properly what it means, but let's just remember that plus infinity is not the same as big O of 1. Okay. What about the Ginibre thing? Okay, for Ginibre is something we can say a lot about. Remember, this is in the liquid phase. Beta equals 2 is after or before the phase transition, depending on where you start, but you're not a crystal anymore because 2 is less than 140, at least allegedly. Well, we know the 2-point correlation. That's actually the only case where we know it. And as you can see, it decays very fast. So in the sense of physics, this is a disordered, it's liquid, it's very fast decay of correlations. And if you sample it, it looks fairly random, right? It's hard to see the strong lattice-like order within that picture. And yet, if you compute the number of variants, it scales like R. So it is as hyperuniform as a lattice. It's as hyperuniform as anything gets. It is number rigid in the sense of Gauche-Perez. So if I sample this, well, an infinite version of it, because in finite volume, it's kind of easy, and I hide a domain, just by looking at what's outside, you can tell me how many points were in the domain. And in this story of distance to Lebesgue, it has finite distance. I didn't do a great job on that part, so let me skip it. But let's just say it belongs to the rigid team also in that regard. So that's surprising. You're liquid, but you have a lot of order in all these features. What about the zeros of the Gaussian entire function? Sorry. So this is G-nib and this is the GEF. Okay, you have to really be trained to tell the difference. They are very similar. Okay, well, same questions, basically very much the same answers. The number of variants is as good as it gets. This one is not only number rigid, but it's also center of mass rigid, which means if you hide a domain, from looking outside, you can tell how many points are in the domain and what's their barycenter. It also has finite Wasserstein distances. So but if you look at it, where's the order, right? Does it look like a lattice to you? Not at all. And yet it has all these very good properties that lattices have. So there's this kind of hidden order, and that's why, so this notion of hyperuniformity, for example, the growth of the number of variants, this has been studied a lot by actually by theoretical chemists. So Salvatore Torquato, who is in Princeton, is a big proponent of this notion, and he calls it a new phase of matter, which might be I don't know if that's an overstatement or not, but the point is that you have this strong notion of order, even though you may have disorder in the usual sense. Okay, so finally, what about the 2D OCP? So I talked about the 2D OCP for beta equals 2 because G-nib basically covers that case. What do we know about general beta? First thing is we do have existence of limit points for the process. And I should emphasize it's limit points. It's not a limit yet. So up to subsequence, right? This is a result by Armstrong and Sarfati. So it makes sense or some sense to talk about the infinite volume to the OCP, at least up to a subsequence. And last year, I published a paper that shows that these limit points, so this is an abstract existence result. It's just compactness in some good space, okay? But they don't describe the limits. And I show that they have a physical description through DLR equations. So I answer the question I mentioned at the beginning, which is the limit P, can it be written like this? So it's not exactly like this, but in a DLR sense, which I will say a word about in a minute if I have time. Plus, I can ensure that they are all translation invariant. So the Mermin-Wagner statement remains true at least for translations. I don't know about rotations, but all these limits are stationary. And as a byproduct of something else, you also get that they are number rigid for all beta. Okay, so that's kind of funny to think about. The translation invariance, well, maybe what I should say is that the translation invariance well, okay, no, let me take that back. But the number rigidity is not something, it's not something you would expect for beta very small, because when beta is very small, you're close to Poisson, and Poisson is not number rigid at all. Okay, but it remains true. And let me skip that part for the moment. The number variance, so the question of hyperuniformity, is also, so it's also true that for all beta, the number variance grows slower than the volume, which is the definition of hyperuniformity. So I prove a little O of R square in a quantitative way, but I just go by some power of log below R square. So this is still kind of far from this, which is what the physicists think. So again, there's a form of order that survives for every beta. Okay. What was known from before, so these are papers by Bauer, Schmidt, Bourgat, Nicolas, and Yao, and by Sylvia and myself, a little bit older, is that if you replace indicator functions by smooth statistics, and you ask the same question, which is the growth of the variance, then you get something much, much better. You get big O of 1. Okay, so for smooth things, you're bounded, which is surprising, right? It's very far from the usual CLT. And for indicator functions, you get little O of R square, so it's better than in IID, and you should get big O of R, but we are not there. On the other hand, as I said, we have no idea about correlation functions, upper bound, lower bound, no idea. Okay. So in the remaining time, I will discuss those things a little bit more, but without giving proof. So maybe just to explain what I mean. What about these limit points? So this result I'm talking about by Armstrong and Salfati. So what do we actually study? You have your system, you pick a point X, which is it's not a point charge, right? It's just a point of the disk. And then you look around X. This is the local process around X, which you could encode with this measure. You have your points and you're just looking around X, so you shift everything by X. This is a random quantity, right? Because your system is random. So you have a random radon measure, basically. And your question is this tight as n goes to infinity? And if you do some elementary functional analysis, so to speak, you realize that you would want a control on the average, or maybe the second moment, but the average is fine, number of points around X. But around X at a microscopic scale. So here, square root of n is the global scale. It's the macroscopic scale. And big O of 1, so the distance between two charges here, is the microscopic scale. And that's what you need. But the problem is that the only information you get for free, or not even for free, is that globally you have a good understanding on the number of points. Well, okay, that's for free. Globally, you have n points with in a domain of size n, all right, of area n, square root n times square root n. Okay, and you would like to go down in scales and realize that in a disk of size 10 around X, you have basically 100 points. Okay, and this is the point of local laws. So if you know random matrix theory, you may know the local laws in random matrix theory. It's the same kind of idea. And you need to do some bootstrapping scales that shows that if you have a good understanding of the system at a certain scale, you can pass it down to a small scale and a small scale, etc. And I had done that during my PhD, and Bauer, Schmidt, Bourgat, Nicolas, Yao also. And Armstrong Sarfati, they revisited those methods in a better way. In particular, they are able to reach the microscopic scale, which is really what you need in order to prove existence of the limit points. And I should say it's existence by compactness in some topology that's not completely satisfying, but it gives you something. My apologies for the smaller slides. Something got wrong with my tablet. I hope you can still see. Okay, so this is the limit points part. Once you have these limit points, you want to, as I said here, you want to describe them, to give a physical description to them through this DLI equation. So what do you need to do? Now you have this infinite volume process, right? You fix some box lambda, a bounded one. And the thing you need to do for DLR is that you need to define what it means to compute the interaction of the system within lambda and the system outside lambda. And here we're facing again the problem that Coulomb is long range. If you have short range interactions, so an integrable potential, this is fine. This is the classical theory of statistical mechanics. You can find it in the book of Georgi or whatever. Then it's fairly easy, or at least it's very doable. Coulomb is not short range, so you giving a meaning to this was actually an old, not a big problem, but it appeared in several as a remark in several papers that it wasn't clear how to do it. And the answer is not super smart. And I just had to wait until the tools were there, basically. So of course, what you need to do is to use cancellations with the background. If you're just trying to compute interactions of the purple points with the purple points, you will have infinite diverging thing, okay? But if you subtract the blue things, well, you can expect some cancellations to happen. And in one word, the trick is, so you want to give a meaning to this, basically. You just pick one point x within lambda, and you want to give a meaning to the interaction of x with everything outside. As you can see, this is a poorly defined quantity a priori, right? It's hard to give a meaning to this. Well, you cut this into, you take a smooth partition of unity and you cut this by introducing these smooth truncations. And then the yellow part here is basically a smooth linear statistics. And then you can import your results on smooth linear statistics, which, as I told you, are very well controlled. So it's big O of 1 depends on which statistic you're looking at. Okay, it's a smooth statistics which has small derivatives. Okay, and that's how you give a meaning to these interactions. And once you have a meaning for the interactions between lambda and lambda bar, so between inside outside, then the DLR equations mean this. You want to say that the law of what is inside, knowing what is outside, is proportional to some Boltzmann's factor, where in the energy you have the interaction within lambda and the interaction between lambda and lambda bar. Okay, so you just gave a meaning to this. That's just the definition of the DLR equation. You still need to show that they are satisfied, those equations. Well, they are satisfied in finite volume. That's fairly easy. And then you need to pass them to the limit. And there's a procedure for it. Basically, if you know how to define this, you will know how to pass them to the limit. And then when you have your DLR equations, you have some solutions. So you prove that the limit points, those guys, they satisfy the DLR equations. You can say, okay, are there more solutions? Maybe there is just one solution when beta is small enough. That we don't know how to do, but it would be very nice because in the classical setting, that's a fact. And then you can ask whether they all have the same symmetries as your finite volume model. And that's the last thing I will say, is this discussion of no symmetry breaking. So what I can say is that there's no breaking of translation invariance. So all this, I should say, there's a slightly plus technical conditions, but all the limit points, so almost all the solutions, and in particular all the limit points, are translation invariant, which is not obvious. I should emphasize, the finite volume model, it has a boundary, right? So you cannot just shift it and you will touch the boundary. If you shift everyone by even by epsilon, it doesn't work, right? So you need to follow older ideas by Fröhlich Spencer in the 80s, and then by Georgi revisited those ideas in the early 2000s. And the technical thing, if is okay, so you cannot just do a global translation because this will have infinite energy cost, basically. You construct a localized translation, so that's something that's a translation locally and then the identity far away. And you evaluate how much you change the energy if you take a state and then apply to it this localized translation. And if you show that this energy cost is bounded with respect to where the translation lives, then magic happens. And I should emphasize, it's really there's something really magic about it, which relies on the fact that the solutions of the LR equations have a nice convex structure, but I'm still sorry. I still have to really accept the magic here. And the difficult part here, I should say, is evaluating this energy cost. So you can imagine you have this Coulomb energy of infinitely many particles, and then you're applying something that's not quite a translation, and you want to prove that it's bounded. But thankfully, in the papers by Sylvia, you have fine estimates on what happens when you apply small perturbations to your system, and that's enough. Okay, so in the 2 minutes, or actually I need 20 seconds, some important questions. Well, I mentioned most of them. We still don't know much about the phase portrait. And one thing that seems to me the most doable would be to prove that when beta is very large, you only have one, basically you have a limit and not just limit points. So and one way to prove that would be to say you only have one solution to DLR. In the classical theory, this is known, but Coulomb is not classical, so that doesn't work. You could ask the same questions with Riesz interactions, so some power laws instead of log. You can do higher dimensional Coulomb. You could try to actually study the correlations if you're super brave. And you could also try to please the physicist of the 80s and replace my little O of R squared divided by log R to the blah blah by big O of R in these hyperuniformity estimates. But I also don't know how to do it. Thank you for your attention.
Thank you very much. Okay, so if you have questions or comments, please just unmute yourself.
Right, if I may. Thank you
But
for
Eric,
the lovely
sorry.
talk.
There was a comment in chat
Oh.
from Sylvia. So I'm sorry for interrupting, but
Yes, I just put a comment, a bibliographic comment, which is that the existence of limit points you can get from the result of Eric Thomas, which is a sort of much shorter proof than the paper of Armstrong and myself. For that, if you're interested in that question, and in particular, it's better because it goes all the way to the boundary, so you can zoom anywhere, not just in the bulk. I think it's worth noting.
So, Ian, I think you had a question.
Yes, just one thing that I got a little confused about. So you mentioned at the very beginning that the conjecture for this 2D model is a crystalline phase for low temperatures, but then you prove that you prove the absence of translational symmetry breaking. So why would you call that phase a crystalline? There could be, as you mentioned, rotational symmetry breaking, but then you wouldn't call that a crystal, would you?
I think that's how they call it by day. I mean, I think they still call it a crystal, and precisely a crystal is not a solid. I think I've learned that at some point, is that a solid would have breaking of translational symmetry, or at least maybe put differently, a slow decay of correlations of translation of positions. Okay, but they say, okay, that's not possible. But what is possible is to have a slow decay of angular correlations, and they call this a crystal.
I mean, I think the term that I heard about for this would be a liquid crystal, the crystal.
Ah, okay. Okay, that's a good point.
Yeah, I
Okay.
think I also.
Okay. I'm happy to change my terminology as I.
But is it really liquid crystal? But usually liquid crystal are made of sort of
Very
non-spherical
rotating
things.
that's
Yeah.
true.
So this is a point particle thing. So I still
Well,
wonder
and
if they
That
have.
seems, I mean, it's very strange that you're breaking rotational symmetry. It's
this happens for 2D hard cores.
Oh, okay,
No.
okay.
Well, in physics we
Just
have both special.
mhm.
And you choose the direction from the boundary conditions. Okay. Okay, but then connected to these, I'm not sure. You talk about liquid phase, but then actually you're saying that actually there is always some kind of order. So what again? So I mean, it's a serious. So what do we mean here by liquid?
Well, that's the question. Is that what do we mean, right? Well, liquid should be fast decay of correlations, right? So that there's at least we know for G libre. For beta equals 2, the correlations they decay like a Gaussian. Okay, the 2-point correlation is 1 minus exponential the distance square. So that's a liquid. I think. It fits the description of a liquid, at least in that regard. But also in other regards, it has a lot of order.
Even though we don't
okay, I
have
should.
this variance or.
No, yeah, all these properties, you don't see the difference. Well, you see the difference in beta in the sense that maybe the variance has a 1 over beta in front, right? But the growth is the same. What do you want to say? Well, yeah, if you run simulations, you see, that's what they did even in the 80s. You see indeed something very clear happening around 140. There is one side which looks like basically like IID points, not really IID, but very disordered, and then all of a sudden you basically see a lattice. But so the visually you have a transition, but for all these questions you don't see anything. Okay, it might be that the numerics is wrong. That's always something to keep in mind, right? Or just shows you something that's not the reality.
So it seems that actually beta equal 0 and beta equal infinity, they are not like, they're not really describing two phases because they're kind of single points and then whatever is in the middle seems to be completely different.
Yes,
And approach
yes.
them.
So beta equals 0 is certainly not a phase, right? The Poisson is nothing. Beta equals plus infinity could be, right? It could be that plus infinity and something close to plus infinity look very much. So it could be that at plus infinity at plus infinity you have exactly a lattice, allegedly. Okay, you will not have exactly a lattice at beta equals 1 billion, but you could have a lattice plus perturbations maybe. And then once you approach beta equals 2, you don't look like a lattice at all.
So there is, okay, yeah, please.
Oh, so it means that there's no simple high temperature expansion. The expansion in beta. Usually in system you can expand in beta, but probably it doesn't work here.
Yeah, I don't know of any result of that kind.
Can I ask a question about your theorem on translation invariance? So you suggested this similarity to the Hohenberg-Mermin-Wagner theorem. But is it just analogy, or is there? I mean, for
no. It's not just analogy. So the older strategies that I mentioned, especially so Georgi is really just a rewriting of Fröhlich-Spencer. Is it Fröhlich-Spencer or Fröhlich-Pfister? Sorry, Fröhlich-Pfister,
oh
not
yes,
Fröhlich-Spencer.
yeah, that's
the proof. So this localized translation is really it is to translations what a spin wave is to spin symmetry. Okay, so in a spin wave, you will rotate the spin and then dampen your rotation. Okay, and in a localized translation, you translate the points and then you stop translating after a while. So it's the same strategy of proof as at least one strategy of proof of Mermin-Wagner in the classical case.
But yours is really long-ranged, so
yes,
puzzled at the same art, sort of same philosophy works.
Well, it's because Sylvia gave us some very good understanding of yeah. So you need to tame the long rangeness and sure.
Okay, very interesting.
Other questions or comments? Complaints?
I asked my question already, but if nobody else has any, I have another one. I find this absence of translation invariant very interesting. Do you think this would still be true for the two-component plasma? Do you have any sense of that?
Maybe Sylvia can, she knows better about the two-component thing, but so the fact that there is translation invariance, right?
Right.
Yeah.
Whether there is, is it?
I don't know. Let's yeah. Sylvia, you don't know either.
Sorry. The translation of various, that's the question. Is it still true? I would expect so, but the situation is much less rigid for the two-component Coulomb gas, because once the particles are paired in dipoles, you lose the long-range nature of the interaction in some sense. So I wouldn't expect at all the same phenomena.
Right, but if it's less rigid, then you would expect less more translation invariance, I guess.
Yes, exactly. Oh, sorry, I thought that's what you meant.
Good, yeah.
Okay, so if there are no more comments or questions, then I close the official part of the seminar, so we can stop the recording. And of course, you are very welcome to stay on and ask all the stupid questions you didn't dare to ask before.